So thank you very much for inviting me. It's great to be here at Nano Days. So my name is Joe Checkelsky. I'm from MIT and also the National Science Foundation Center for Integrated Quantum Materials. And I will try to tell you in my life as a physicist and a so-called quantum mechanic how we can try to make new kinds of materials towards realizing something called a perfect conductor. So a perfect conductor, if we could realize it would be something that could save tons of waste heat energy in modern electronics and maybe even change the way we do quantum communications and different kinds of related technologies. So to tell you about new kinds of quantum materials, I should first start with a much more conventional material that conducts electricity, which is copper. So when you plug a light bulb into the wall, electricity is carried through a wire, which you might already know is a simple kind of metal called copper. So copper is a very good metal, and it's pretty efficient, but it's not perfect. So to explain to you why it's not perfect, we have to look a little bit closer. So if you actually zoomed in very deeply into a normal material, what you would find is that most of the electrons are actually orbiting around some ions. The ions are vibrating back and forth because the material is hot, and some of the electrons are actually allowed to move from one side of the sample to the other, but it's not very perfect motion. You might have imagined that when you plug something into the wall, the electricity just rushes across, but it's actually quite a bumbling path from one side to the other. And every time you get one of these collisions between the white electrons and the ions, you get some heat. And so I'm trying to get energy from the left side to the right, but along the way we're actually dissipating a lot of it, right? So when you have this kind of system which loses energy, there must be some way to improve it, right? Without that, what we have is, for example, computers. If you use a laptop and you put it on your lap, it gets hot after a while. This is uncomfortable. So there's much grander scales at which this is an issue. This is a picture on the left of a computer server, right? And these things tend to be stored in really well air-conditioned data centers. This is a thermal picture on the right. And what you can see on the right is even though it's a nice 65 Fahrenheit temperature outside of the machine, it's sort of red hot inside. So this is basically energy being lost in computing. So this problem is getting worse and worse because, for example, in modern day data centers, you have many of these kinds of computers. And it's estimated at something like 100 or 200 billion kilowatt hours of energy is being dissipated in these things every year. This is like 2 or 3% of all of the energy used in the United States. So this is going to get worse and worse as there are more data centers in the US and around the world. But actually there's something that's even more troubling. The way we transport energy all across what we call the power grid in the US is through these copper lines. And in the US it's not so bad, but in some countries up to 10% of all energy that is produced is just lost in its transmission. So in order to sort of improve on this, you could think of a lot of different ways we could approach it. So before doing the quantum materials approach, we can do a simple experiment. And for this experiment, I have to wear goggles because we're going to use something very cold. So instead of just cooling down our computer servers with air, which is around 60 degrees Fahrenheit, we can cool them down with liquid nitrogen. So if we cool something down with liquid nitrogen, that's at around minus 300 degrees. And to simulate a lamp, I have a very simple lamp here. There's just a wire. There's a light bulb. Right now, I can run a bunch of current through it and see what happens when I put it in the liquid nitrogen. So what do you think will happen if I put a lamp in the liquid nitrogen? If it's a little bit bright and I put it in, does it get brighter? Does it get darker? Does it explode? We have to close the museum because of some disaster? No, none of these, right? So what happens is that we've poured some liquid nitrogen in. Good, Megan's got it. I can turn this power supply on. There's 10 amps of current, but you really can't see any light until I put it in the liquid nitrogen, and then it starts to light up, right? And so when it gets brighter and brighter, this thing's actually getting colder. What's going on, I can show you a simple animation, is originally the ions are bouncing around a lot, but when you cool it down, this vibrational motion calms down, and now the electrons can move much more easily from left to right. This is kind of a reversible process. If I take it out of the nitrogen and allow this thing to warm up, and if I'm very brave and warm it up a little more quickly, right, in the spirit of time, you see that the light gets dimmer and dimmer. And so what's happening at the same time is this current is running through, there's more of these collisions, and all of a sudden the light almost goes out. And the system becomes much less efficient. I can make it more energy efficient by putting it back in the liquid nitrogen, right? But as soon as I take it out, I lose it all over again. So we could, in principle, save a lot of energy by always storing all of our lamps in liquid nitrogen, right? But the obvious problem is that we don't get this energy for free, right? Actually, it costs a lot more to produce the liquid nitrogen than we save from putting in this light bulb. So there's a very different approach to this rather than using this kind of cryogenic engineering, and it's using something called quantum materials. So there's another kind of material that's made out of copper, but also has some yttrium, barium, and oxygen in it, and we can show you a demonstration of it. So what this looks like at the internal level is that instead of having electrons all moving as classical particles, this thing is called a superconductor and acts like a big quantum condensate. So all of the electrons, instead of having individual personalities like when they were those little white particles, now they behave as this kind of quantum collective. It's just one object that moves from the left to the right. So first of all, not only do they have zero resistance, right, but they can even do much more dramatic things. If they have zero resistance, you wouldn't be surprised that you could conduct electricity with no loss. But even because of the way they interact with magnets, you can actually make them float. You can even imagine making things like frictionless trains. So we have another demonstration of just having one of these superconducting magnets, which Megan can bring a little bit closer to you. And you can see that actually the superconductor is completely locked to the position of the magnet. And it's a good example of having some property of a material which you first would not have expected, but what we refer to as some emergent phenomena in a quantum material. Right, so it's just hanging above the magnet. She can move it around as she pleases. Right, it's a really surprising thing. Superconductivity was discovered more than 100 years ago. Sorry, Megan, but it wasn't until basically the 1980s that we could do this just with liquid nitrogen. So, thank you very much to Megan, my assistant, for helping with the liquid nitrogen. As soon as she leaves, I can take the glasses off. I'm very excited about it. So what I can show you, for example, there was a lot of excitement in the 1980s when this was first found. As I said, superconductivity had been known for 100 years, but being able to do it, which these guys discovered a new material in the 1980s, generated a lot of interest. You could levitate heavy things, heavy people, for example. There's even modern technologies where people have tried to turn these things into trains. And even more recently, people try to develop real wires which could carry electricity perfectly. So we call them, sorry, I forgot about the glasses. So we call these things high temperature superconducting cables. So the only problem is really basically the same thing as we had with the copper. Liquid nitrogen is expensive, this cryogenic engineering is difficult, and still we haven't realized a widespread implementation of these kind of materials. Sometimes we use superconductors. For example, if you've ever had an MRI, it has a superconducting magnet, but in most cases this is still too expensive. So what I want to tell you about is a very different way to try to get at this perfect conduction by doing a little bit of quantum engineering. So I want to tell you about building materials. So building materials is not really that different than building a house or building a structure. There's sort of two basic considerations: what materials you use to build the house, then how you actually put them together. So do you choose steel or wood or bamboo, and how do you layer them together? Except instead of working in this space for buildings, basically we think about structures for crystals, and we think about the periodic table for the elements. So sorry, it's kind of a boring looking periodic table, but the reason I chose it is all the ones in yellow are the ones that we have used in my lab to try to make some quantum material, and the blue ones are sort of pending in the furnaces now, right? We're sort of afraid of the radioactive ones in the bottom, but otherwise, it's a really sort of vibrant space to work in. Right, so I don't want to talk about trying to build these three-dimensional things. That's a little too complicated. What physicists and mathematicians usually do is try to think of a more simple problem. So instead of talking about building a house, we'll think about building a material the way you would tile a floor. So the simplest way to tile a floor is shown here. It's just a square pattern. Someone in a mathematics department would make it look even simpler and just say that the way you can describe this pattern is it's 4 to the 4th power, and meaning that it has at every little one of these points in space 4 squares joined at a vertex. And the simplicity of that construction is that every vertex you look at is the same. A kind of curiosity-driven question is, what other ways could you tile a floor? So actually, if you want to use regular polygons, there's only 2 other ways. Either you could do it with triangles and hexagons, so-called 3-6 or 6-3. If you relax things a little bit, there's a few more interesting patterns, right? So these things are regularly realized in tiles on floors. There's actually 8 more possibilities if you allow yourself to use different kinds of polygons. And so by using regular different kinds of polygons, there's these 8 different ways you could tile a floor without any cracks. So these are referred to all together as the Archimedean tilings. Supposedly this is something that Archimedes came up with. There is no historical record, actually, but maybe that's because some old museum burned down. So hopefully that will never happen again. And so actually Kepler in the 1600s talked a lot about this. It's the first historical reference that is actually somewhere on paper, right? So you might ask the question, you thought I was a physicist, why am I talking about all these graphs and math? The big idea is that the things that we can actually make together mathematically in a systematic way are the same things that will appear in nature. So the things we can build by hand and make tiles, but they're also the same things we can use to make real electronic materials. So to give you an example of one that looks pretty esoteric, this is 3464. So it forms this funny pattern with squares, triangles, and hexagons. You can find it some places in Spain and churches on the floor. It doesn't exactly look right because of the way the photograph was taken, but if you use Photoshop to make a projection, indeed, this is the same shape. So not only can you make it as a floor, but actually, for example, in my lab, we can make electronic materials, which are composed, for example, of bismuth, rhodium, and iodine, which have an atomic structure which exactly maps onto this. And it's interesting that by abstracting away to the mathematical structure underneath, we could really predict a lot about what a material is going to do. And even on the macro scale, this is a crystal grown on the right, you can see some remnants even of the hexagonal structure, even in kind of a grand scale. So an important prediction that is going to drive the thing I'm going to talk about was made starting in the 1980s, particularly by two theoretical physicists, Duncan Haldane and Charlie Kane, who said that if you consider lattices which are composed of hexagons, then under certain circumstances, instead of all bumbling through the inside of the material, the electrons could actually flow perfectly along the edge, right? And it was a very different kind of conduction that they predicted. So it turned out that they wanted to use these hexagons. There's something important about the way elements are connected in hexagonal networks. But in a quantum mechanics sense, it's actually pretty hard to fill this lattice with a lot of different elements. So there's one other lattice which is a little more friendly, which was already introduced. It's the idea of something called the Kagome Lattice. In the math language, it's just this 3-6 squared or 3-6-3-6. It's everywhere hexagons and triangles. It appears in medieval Islamic art from the 13th century. And also, in a more well-known case, appears in a kind of Japanese basket weaving. So allegedly in this picture, there's a bird somewhere inside. I guess it's good for traveling around. They can put their beaks out of the hexagon. I don't know, right? But this pattern shows up in a lot of different places. So a theoretical prediction from some of my colleagues at MIT was that if you could fill this particular lattice with something magnetic, you might be able to reach towards this kind of perfect conductor, which you could do it using magnetism. So instead of superconductivity, which for example needs liquid nitrogen, we all know that at room temperature, kitchen magnets stick to the fridge. And if you could use that kind of energy scale to make a perfect conductor, it might make a really new, exciting kind of breakthrough. So how do we actually make this kind of material? So we start with really high purity elements. These are just mined out of the ground and refined. Just iron, for example, which is magnetic, and also very high purity tin makes the sample a better metal. The way we actually make a material, you just take them, you grind them up with a mortar and pestle until they're nice and ground together, and then you melt them in one of the, for example, many furnaces we have in my lab. So we can heat up to, for example, in this optical furnace to 3,000 degrees Celsius, half the temperature of the surface of the sun, and then if you cool down slowly, you can make a crystal. So one special thing about this material I'll tell you a little bit more about is it's a little bit stable, but we actually have to do one trick, which is to take this material when it's really hot and they're combined at about 800 degrees Celsius and then bring them down to room temperature very quickly. So this is a common process where basically we use a bucket of ice water, but people in the steel and titanium industries use these very, very exciting things where they have big buckets of water and they pull things out of their furnaces and cool them down very quickly. This is basically what goes on in my lab, except I think we have slightly better safety equipment. The guy's not even wearing gloves or glasses or anything. So the students do a better job than this, but basically they open the furnace and they can kick the things out into a bucket of ice water. So I'll tell you in a minute why this is important. So by doing all this process, we could actually realize these little crystals. And again, they're this iron Kagome material, which has a little bit of tin in it. And the reason that we have to put tin is if you'll notice, if we only had the iron, there are these big empty spaces where the hexagons are. So this wouldn't be stable because nature really likes to fill up materials. So we had to add some tin to the center of the hexagons. It's still not quite stable enough, so we have to do this quenching process. So in an ordinary material like I showed you before, the electrons are all bouncing around randomly. So this is something with whatever, a 4-4-4 pattern. If I make some sort of analogy to driving cars, right, these guys are bouncing around everywhere and not making it through smoothly. So this new material does something a little bit different, right? We have to instead make it out of this Kagome structure. So the perfect Kagome structure, like I said, would have all of these hexagons and triangles. It's got this 6-3-6-3 setup. This one isn't particularly stable, but what we can do, for example, to bring magnetism in is instead of having these atoms which have no net angular momentum, we can fill the lattice with these red atoms, which represent iron, where the electrons are only going around in one direction. To make the structure stable, then we can add the tin element into the center of the hexagon, and now it's kind of filling space everywhere. So this was our quenched material, and then when we run some electricity through it, instead of all bumbling through the inside of the material, most of the current can flow along the edge. And it flows along the edge like a highway. You know, the electrons going one way are on the bottom and the other way are on the top. They can even move a little bit around the edge. In our real material, there's still some electrons bouncing around in the middle, but we have evidence anyway that they're moving along the edge. So then to make the car analogy, right, now the guys are moving the other side of the way on two sides of the road, and we don't get as much scattering between them anymore, right? This came out a week or two ago. There's a little bit of coverage for it, some of it more broken than others. So to give you an example with this BBC News, we were not precisely inspired by a Japanese basket necessarily. I mean, it's a mathematical pattern that is shared by these Japanese baskets. But one of my friends from Europe sent me this article on the right, which I couldn't figure out was about our system or not. But then they showed a picture of this Japanese basket. So indeed, I guess this is the common theme. So it's anyways just an example of using this lattice to make a real conducting material. The thing that I like the most about the coverage, so this is just a photograph from my office with the main people who were involved. A student in my group, Linda Ye, a colleague of mine, Ricardo Comín, and his student, Minggu Kang. The most important thing you can see behind us on the chalkboard is us drawing this Kagome pattern again, right? It's just triangles and hexagons. And the idea is that we can fill this pattern with all different kinds of elements. This picture on the left was taken by our colleague David Bell, where you can actually see the electrons in the pattern. He's not looking at the triangles and hexagons, he's looking at it from the side. You can see them all stacked up. We could stack these materials in different ways, we could put different elements on them, and we're hoping what we can do is by making more and more pure Kagome metals, we can finally realize this dream of putting these electrons on this perfectly conducting electronic superhighway. So thank you very much for your attention. These are all of my collaborators. Thank you.